Okay, Exploratory online seminar number 75, a grammar of analytics, model agnostic interpretability for machine learning. These are the agenda. I'm going to start with the prediction model and the grammar of analytics and the correlation and the causation, multivariate analysis. And the last, I'm going to touch upon a little bit about a difference between statistical learning and the machine learning models. So let's start with the prediction model, what the prediction model is. This is a brief description of the prediction model. It is really a formula or a set of rules that are defined by algorithms based on the patterns that algorithms identify in the past data in order to predict future or unknown. So it doesn't have to predict the future to predict. It might be like past data, but somehow like you don't have the answers. So you might still want to quote unquote predict to fill the answers. So prediction model, that's more like kind of inner working. So like you have the data and that have answers, can be the sales, can be, conversion status, converted or not converted. And then also we have the data of other type of variables, such as users' demographic data, or maybe like a time spent on the website, what button clicked, and so on. And then have the algorithms find the patterns in the data. Basically, the patterns is about the relationship among the variables, and then identify the based on the identified patterns, and then define the formula or set of rules, and then create that model, and use the model to predict the answers for the data with no answers. So use case, the common use case is that we know it's like our business, right? So like you have the customer data, and we know who converted, who have converted, who have not converted. Then by using the customer's attributes, let's say it can be the age, can be the which page this customers visited, how many times they spent on particular page, and so on, and then build a model. And then once we have that model, then like you have the new customers, and then you can use the model to see if this new customer will convert or not. And then because that's useful, because once you know that type of the probability or the prediction, then you can focus on which customers, decide which customer to use. You should spend more time and energy and so on. Okay, so here is a customer data. And each row represent each customer, and the customers maybe age and time and country and industry and so on. And then the left-hand side is the conversion column. And that is what we are interested in or we want to predict, right? And then the rest of the columns, well, like the customer's demographic data or attributes data or usage data and so on. So we call them in a very specific name. So one is a target variable, and that's the one that we are interested in. And then prediction variables, those are the ones that we wanna based on, and then we wanna predict the target variable values. So in a graphical way of showing this is that, so let's build a model. That means you have the data that we saw, and then we feed the data to algorithm. The algorithm identify or recognize the patterns in the data. And then based on that, it will build the model. Can be a formula, can be a set of rules. And then once you build a model, then you can feed that data that doesn't have the answers yet into the model. And then the model, you will use like the customer attribute data, attribute information in this case. And then based on that, I can just go, each row basically goes through the formula or set of rules, and then we return the probability or the value, predicted values. Okay. And then it can be like each row, hey, this customer might be true, might not false, might be false, and so on. In particular, this case, though, usually the model doesn't return true or false. Model return instead the probability. Like this customer will be like 55% of the chance it will become true, or 95% chance it will become false, or something like that. Okay, so that's how the prediction model works. But this person called George Box, who is very famous, well known in the world, especially in the world of statistics, but also like in data science. And he said a long time ago, all models are wrong, but some models are useful. And I think this quote is very, it's kind of it's deep. It's very insightful. But how I interpret this quote is that it's with the model, the moment you build the prediction model, the prediction model is, when you think about it, it's kind of like a very simplified world of the actual very, 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 very complicated world that we live, right? So no way the model can be right or correct. I mean, there gotta be like something already wrong, right? So there's kind of a simplification of the world in a way at the end of the day. So for that matter, it's already wrong, but still some of the models are kind of useful, like you can still use it to predict and what's going to happen in the real world. But I think it's more than that. Is this quote means that it's not really about predicting the future, but I think it's we can understand more about the past, what are happening in, let's say, the customer data, what are the variables, and then what are the variables actually have anything to do with, in this case, the conversion or maybe sales and so on. We rather focus on, instead of focusing on the future itself, like let's understand the current or even the past first. And then on top of that understanding, then we can start inferring, what is going to happen in the future, even like without using the machine. Like maybe like with that insight, we can see like what we need to do. So having said that, data, algorithm, and a model, right? So these are the ones that sort of basic sort of like workflow of the machine learning or statistical learning. But I think what's really important is what kind of knowledge we can get out of that prediction models. I think that's the most important part. And then because we can ask these kind of questions to the model actually once we build a model. So something like which variables have stronger relationships with a target variable compared to other variables, or how that relationship works. I mean, it's like what happened like if the customer spends more time, and then the probability of the conversion increase or decrease, and if it increases, like how much increase, and if there's any limit of the time spent, and so on. And also another thing is like as those changes are significant, let's say like this user spent 10 minutes more, 1 hour more, and so on, that will influence maybe that have like some kind of correlation with the conversion. But is that relationship is a significant relationship, or it's a marginal relationship that we shouldn't even spend our time and energy? Or so last one is like how much of the variance of the target variable, let's say like how much change in the probability of conversion, how much change in the sales can be explained by this prediction model. And again, when I said prediction model, it's really a set of the variables. On top of those variables, we define a formula and a set of rules. So if we build a prediction model, can we really reliable on this thing? Like how much of that changes in the target variable have something to do with it? So these are the things that we can investigate once by building a prediction model. Okay. Then the prediction model in exploratory, I mean, like exploratory provides various prediction model types, but in the world of data science, there are tons of others. But even like with this set of prediction models in exploratory, like if you're not familiar with these things, and it's kind of like overwhelming, hey, like which one I should use? So it's really, at the end of the day, like it comes down to it, is depends on like what you are interested in. Okay, so these are the algorithms, and there are more others that couldn't be captured in this picture, but it covers many of them, and you can find in exploratory. Okay, so these are like all the analytics types. And then blue color is unsupervised learning. So that's not really the topic of today. Today is like prediction model, which means supervised learning. That means that based on the data with answers like sales values or conversion status and so on. And we want to build a prediction model to predict the predict answers. Okay, so that is a green or orange. Green means the statistical learning models. Orange means machine learning models. I'm going to talk about that difference later on. But in this case, it's pretty much the same thing. And in fact, in the world of data science, many people call all these green and orange thing as a machine learning. And I'm not really, I don't want to get stuck on the wording and definition of the literature types of things. But so in kind of like a loosely defined, they're all machine learning. So out of these, like if we focus on these areas, so these are the areas like prediction models. Left-hand side top is like a Prophet, ARIMA. Those are also prediction models, but those are like a specific type of prediction model called time series data. So that's not, we are not covering this today, but we are talking about this area. So when you start at the center of this picture, then if you want to predict something like numerical values, like sales or salary and so on, then you want to go to the left-hand side. So now like you can use linear regression, GLM, decision tree, and so on. If you have you want to predict something categorical, let's say the customer conversion. The customer conversion is like a true or false. So the customer converted or didn't convert. So it has only two set of values. In that case, the right-hand side bottom, and then go to the logistic regression or decision tree, random forest, and XGBoost. If the set of the value can be more than two, meaning like 3 or 4 or 5, then in that case, right-hand side top. And then green is multinomial regression, and then orange is decision tree random forest XGBoost. And then if you are interested in something more like a charm or cancel type of data, cancel itself can be like a true or false. It has only two set of values. However, it's really important to consider the time it took before cancellation. So for example, like the person who cancel, first month after they sign up, or 1 year after they sign up, or 3 years after they sign up, the meaning of the cancel varies, can be very different, right? So time, how long does it take is before the cancellation is also important. So in that case, we use, you want to use a survival analysis prediction models, such as Cox regression or survival force, which is the center at the bottom. Okay, so these are the things. So this is kind of like out of all those analytics, maybe like one sort of magnification. But having understand this is that it really comes down to it's sort of like a data type, right? So if it's a numeric, then linear regression or random forest. If it's true or false, logical, logistic regression, random forest, and so on. And then I'm not we don't have here like a 3 or 4 values things. We want to focus on this 3 type of data. And then the right-hand side, the true, false, not only cancel or not cancel, but time is important. That type of analysis, then you want to use Cox regression survival forest. Okay. Then now that we know like what type of the analytics types or analytics model, prediction models that we can use to do certain type of jobs. Now let's go into the grammar of analytics. So this is a grammar that we define, but not just we came up with from nothing. Like it's sort of like you might see similar things in the world of data science, and people have kind of similar idea as well. That we difference a lot of stuff. So it's not really like this is completely our new idea or anything like that, but we just kind of use a lot of information and then we build it in Exploratory in a consistent way. So based on the data type, right? So like numerical, logical, and time, those are the ones that we are interested in or we want to predict. Okay, so once we have that, then like a green box is a statistical and then purple box is a machine learning model. And then in each box, like a bunch of boxes, but focus, let's look at the linear regression, which is the most left-hand side. And then there's the other smaller box that says variable importance, prediction by variables, and coefficient, sum, and summary. And then when you look through like horizontally, it's actually like any model, I mean, any algorithm type, you have always the same things, which is variable importance. And that is not just a statistical model in the green, also like a purple machine learning. But also it doesn't matter if it's the, the interest is numerical or logical time, it's always variable importance. And the same thing, the prediction by variable, that's wherever you go, you always have this. The something different is here. This is a coefficient, odds ratio, hazard ratio. You find this information. These are, by the way, the information I'm going to demonstrate after this. But you can find when you build the models. But anyway, so these coefficient, odds ratio, hazard ratio, these things exist only in statistical model. That means you don't see them in a machine learning model. And also the one I skipped, which is the survival model, the right-hand side 2 box. There's a survival curve box that I skipped, but those are only for the survival analysis. And today, I'm not gonna go into the survival analysis of survival models. I'm gonna focus on this numerical and logical stuff. But if you're interested, like I have done the survival analysis seminar in the past, so you can see more detail on there. I think it was like called cohort analysis. Okay, so then the last one is a summary. This is where like you can evaluate the prediction model's quality. Quality meaning mostly like how much you can rely on this prediction model if you end up using it to predict the unknown data. Okay, so that said, basically we have these information, like a pattern of this information. So any model, like when I said like model agnostic, that means if it's random forest, decision tree, logistic regression, whatever that it is, always this set of information, right? Except the coefficient, right, second from the right, that doesn't exist in machine learning model. But other than that, like it's always like these are the information like you want to look at. And then, so first, let's start with first, variable importance. And what this one is that you can answer the question like which variables are more important than the others in order to predict the target variable, the something variable of your interest, right? So then you can see, sort of like a bar chart, and you go to the importance tab and see. So let me actually to touch base on this one. Like, let me just create something prediction model here. So anyway, so this is the employee data. Okay, and then as you see, there's a 26 column and 1,470 rows. That means each row is each employee. Therefore, 1,470 employees data. Okay, and then now we have when I scroll here, there's a monthly income. So this is basically like the salary, right? So like how much each employee is making. And then like other information, for example, something like job role, like what type of the job roles they are, what is the gender, what is the age, and so on. Okay, another important information here is attrition. This indicates this employee has left the company or not left the company yet, type of information. Anyway, so these are the data. This is the data. Then, like, let's say, like, I want to build a prediction model to predict the income to see, like, what has influenced the income. Like, what are the variables that have a relationship with the income, right? So, in order to do, like, I can go to the analytics. I'm gonna create from scratch, And then first thing is I'm going to select, in this case, you remember, it really depends on the data type. In this case, the salary or the monthly income is a numeric type, right? So if it's a numerical type, then like I can use a linear regression, or I can use decision tree random forest XGBoost as well. Today, like, let's say like a linear regression. And the target variables, which one to use? Well, this one is a monthly income, right? So that's we are interested in. And then what are the predictor variables? So here we can actually select from age to all of them. I'm not going to use start date and end date, but other than that, like, I selected all of them. And then click OK and click Run button. And then the new prediction model has been created behind the scene or in the system. And then what we are looking at is that basically the information, we're extracting information out of that model. Okay. One thing though, this is kind of outside of the analytical grammar of analytics, is that this is a statistical learning model. So especially we need to pay attention. So it's something called collinearity or multi-collinearity. What this means is when you have predictor variables, okay, meaning like age and performance or martial status or whatever, if you have these prediction variables, and then if there's some strong correlation among the predictor variables, let's say, I'm not sure, but like, let's say like this age and maybe total working years, if those are pretty much the same information, that means if you know the age, you know the working years or something like that, then that's a strong correlation. It's almost like the answer. When you have something like that, what happens is, especially statistical learning model cannot produce certain I'm going to cover that a little bit later, but coefficients, or in this case, a slope, because there's something like that. Basically, the linear regression is building the model, and the model is a formula, right? And then the formula means it's, for example, in this case, like, monthly income equal slope or coefficient multiply age plus attrition, coefficient multiply attrition, and so on. So those coefficients will become unstable, meaning it can be 2, it can be 3, it can be 5, but somehow different formula can produce the same result of the prediction. I'm not going to go into the multi-collinearity today because of time limited time, but the nutshell you have to be careful is that when you check this collinearity tab, and any variable which shows greater than 10, that means you want to get rid of the variable one by one. So in this case, for example, like I have a job role and department, and then both of them are like way beyond 10. So what I need to do is I need to take this job role or department. And it really depends on like what you want to look at. In this case, let's say like, you know what, like I want to understand the relationship between job role and monthly income. Then I don't want to remove this, because if I remove it, then I can't evaluate that relationship. In that case, I can actually remove department and then rerun this and then see if job roles still go beyond 10 or not. And this is actually a kind of a side thing, is that job role, department, what are these guys, right? So I'm going to just quickly visualize the relationship between those two. Not even visualize. I'm going to just use summarize table or something quickly. So here, like if I have the department and then job role, as you can see, these are basically hierarchical data, right? So that means if the job role is human resource, you know the department is 100% is a department of human resource. If this person's job role is laboratory technician, then that person's department is 100% research and development. Only things that it's not 100% like, being able to say that what the department is the manager. Manager exists in human resource, research developer, and sales. But other than that, basically, if you know the job role, you know the department. right? So that type of relationship is like very correlated or associated. So that's why like we want to get rid of one of them because one carries the other information basically. So in this case, I'm gonna get rid of the department here and I click OK to run the build model again. And then at this point, it's kind of close to 10, but it's not going beyond 10. I'm not the fundamentalist, so like I'm not saying like if it's 9.99 is okay and the 10.01 is not okay, that kind of stuff. So there's some nuance there, but it's not like a major problem, so it looks okay. Then like we can start interpreting this prediction model. So you remember, like I said, like start from variable importance. So here's the importance tab. And then this basically gives you information like which variables are more important than the other in terms of predict, in this case, the monthly income. And it said, hey, job level is the most important. And the next one, the job level is the most important. And the job role is the second, and the total working years. And the other is more almost like nothing. You can't even see. Okay, so pretty much the first two deciding the monthly how the month can explain how the monthly income changes. And then not even two, it's almost like just a job level or something. And when you think about it, it's kind of course, right? Like if you have the higher job level, you get a higher income. So it's kind of like a stupid example, but I just wanted to give you the kind of very simple way of understanding what this is. Okay, so now we know that these three are important, and especially the first two are important. And then so like the next question would be, so how that job level and the monthly income relationship like? How that job role and the monthly income relationship like? What I mean is like what happened the job level is for, like what the monthly income would be. What happened the job role is laboratory technician, what monthly income would be. So that is something that you can go to the prediction tab. And then this one, it says prediction, but it's not like the prediction for each employee, and that not that sense, but it's more like by variable. So if if you know the job level, then like what would be the monthly income? So in this case, so for example, if job level is 4, then this is kind of average, but it says 2,000. Sorry. At the bottom in this pop-up, monthly income is 11,801. So that's about, if your job level is 4, then this is the average income that you can expect in this data or in this company. Okay, and then, but when you look at this chart though, like this blue line is the predicted values or prediction. Okay, and it's always this blue line is a kind of constant slope. It's straight line. It doesn't go, change the slope of, for example, like flat and going up and going down or anything like that. It's always constantly going up or going down. It's in the same way. And then this gray line is the actual values. So this has nothing, gray line itself has nothing to do with the prediction. You can actually go to the chart to draw this gray line. And what this gray line is like for each job level, what is the average or mean of the salary? Okay, so it's that simple. And then you can compare what the prediction and then this gray line. Okay, and when you look at it here, though, the prediction line is kind of aligning with actual values for the job level 1, 2, 3, and then gets kind of separated after the 4 and 5. I'm going to explain why these areas are separated instead of like getting closer. I'm going to explain that a little bit later in the multivariate section. Okay, and here, job role, that's also, this one is a categorical, that's why it's not line. If it's a numerical variable, job level, total working years, those are numerical data types, therefore it's line. But it is a categorical, so there's no point of like connecting those dots because they're not like continuous values. So that's why it's a dot, but it's, this one is, it's kind of hard to see, but each, basically the gray line is the average of the each job role salary, and the blue line, a blue dot, is the predicted values. And again, here, these job roles are kind of closer to like actual values, but then this one, for example, manager and research director, somehow it's kind of a wide difference. And I don't know why at this point. I mean, I know why, but I'm going to explain that more detail later. But at this point, so something you can say like, okay, like what the research directors, if you know this person is the research director, then you can expect an average or mean $10,360 and so on. Okay. So this is the, I kind of already went ahead, is a prediction by variable. Okay. And then in this case, like I'm talking about, we are looking at the numerical data type as a target variable. But what happens if it's a target variable is logical, like converted or not, that type of data? Well, in that case, it's basically the same way. You're going to see that you're going to get this prediction tab and see the similar information, except the y-axis. The y-axis we have been seeing is a monthly income, right? So it's like a $10,000, $12,000, and so on. So value itself. But if you're predicting the logical, like attrition, the conversion, or something like that, then the y-axis is the probability of being true. So, what is the probability of converting, or what is the probability of quitting, or something like that? Okay, that's the only difference. Other than that, basically the same. How the variable target variable change based on each of the predictor variable. Okay, so the next one, the coefficient. So again, this is available only for statistical learning model. So if you're using a random forest or XGBoost, you don't even have to worry about this. One is that you don't have to worry about, so like it's actually easy to start with without this. So it's much easier to start with a random forest in terms of like understanding what the model is saying. But the one downside of that is the variable information in this chart or in this tab, but you don't get that when you use a machine learning model. So that's the sort of pros and cons. But anyway, under these tabs, these are the things you can know. So how much would change in a target variable when a given prediction variable changing 1 unit? In this case, I'm going to just talk about that a little bit later. The other question is a change significant or marginal? It's more, if I'm allowed to super simplify, you need this one just for this reason, which is if that relationship is significant or not. Other than that, basically same kind of information you can find in the variable importance and a prediction by variables. Okay, so we are using a linear regression. So what we can find is a slope or coefficient. So let's see. Let's go to the coefficient tab. Here's a visualized version of, by the way, here's a coefficient coef dot table. That means the coefficient table. You want to see, if you want to see those information in the numbers, then you can go here, or otherwise basically like this coefficient and then the confidence high, low visualize under this coefficient tab. Anyway, so this one here, what it says is, let's start with the job level here. If the 1 unit increase, that means job level 1 increase from 1 to 2 or 2 to 3. In average, you'd expect that's the second one, the coefficient, $2,765 increase in the monthly income. The other one is, for example, here, total working years. If you work extra 1 year, then you can expect that's a second one coefficient. That's like $45 increase. Okay, and then that's basically what I'm talking about here. The coefficient of slope is that this is a slope. So for example, 1 unit increase is from 4 to 5, and how much increase, right? So that's the basically difference between the 4 and 5. Okay. So that is the coefficient, the value that we saw under the coefficient. Same thing for total working years as well. Like if you one increase in a year, like 1 year increase, like how much monthly income would increase, right? Tricky thing is that the categorical variables, what that means, like one value in 1 unit increase, because 1 unit increase in job role, what are you talking about? Well, in categorical case, you are comparing between the values. What that means is, for example, if I go to the coefficient, and here what we can see is this is a job role, and then all the values of job role becomes a variable name. So, for example, in this case, the job role and research director. And then it says base level, second row, says sales executive. So it's kind of interesting. The categorical variable case is like only one variable, which is exploratory, the most frequent value. So in this case, happen to be sales executive. When you go to the summary view, and when you look at the job role, sales executive is 326 people. So that is the most frequent value. So that becomes the base level. What that means is when you go to the analytics, I think this is easier. When you go to prediction, you see the sales executive, where is it? Here. Okay. So as linear regression, define this to be the base level. And the 1 unit increase in the job role means, precisely the 1 unit increase in research director means comparing from sales executive to research director. So what's the difference between these two? And that is the coefficient research directors, this value. So this is, it says $4,103 $4,103 difference between research director and sales executive. Same way here, the job role manager compared to sales executive, their salary is $4,222 higher and in average. Okay, so that's a little bit different in terms of understanding, but basically the same thing. It's like how much increase based on the changes in the target variable. Okay, but so that's once we understand that, the next one is more important, because whatever I've been talking about right now in the last couple of minutes about the coefficient, you don't need this. You can go to the prediction and see the basically the information in a visual way, and also the coefficient number itself is in a pop-up. So like you don't really need to go to the coefficient tab. But there's one thing that you might want to consider going there is that the color. So the blue is positive, so that means increase. Red is negative, that means decrease. Okay, the 1 unit increase in the predictor variable affecting the whatever the value decrease in this case monthly income. But another one is this gray color. So gray color is in the legend, it says p-value is greater than 0.05, which means greater than 5%. But what that really means is that those are like not significant. So if it's significant blue or red, and not significant gray, what do you mean by not significant? Well, there is some changes, some kind of relationship is observed in the data when you go to the chart view, when you create a chart, maybe like there's a two bars in a bar chart. And there's a slight difference between these two in terms of monthly income, like mean of monthly income. But if let's say like if it's $50 different, is that really important? Is that really we have to pay attention? Because we are talking about like, okay, if these two variables are related, let's do something about it kind of situation, right? And then, or, maybe communicate to others and look at that more in the detail. But if it's like, let's say like $50, how about $3 different compared to $500 or $400? For example, here, job role, we're talking about $2,700 difference. And then when someone comes up and say, "Hey, these guys these job roles are different, but between them the $5 difference, so that's not fair," or something like that. Then that's just a waste of time, right? So that type of things you can find here in a statistical way. It's more, like I explain a very casual way, but it's more statistics than that. But anyway, so what it says here is, for example, look at the age. the coefficient is -4. That means 1 year increase of the age. Then you can see the monthly income to be different, like $4 difference and like $4 decrease. So there is, you can say like age might have something to do with it, but then the -$4, who cares? That, you know, is that important? And then obviously this is a gray color, so it's not that important. And then behind the scenes, there's a hypothesis test is done. And that's why this p-value thing. But the more important thing is, to me, is a confidence interval. So confidence high, low. Here, I'm going to just zoom in a little bit here. Okay. And then when I see the age, one thing you notice, which is that it's crossing the zero line. And what is the coefficient zero means? Coefficient zero means slope is zero. So what that means, whatever the value you get in, let's say, age or job level or whatever that is, the line goes horizontally. Like that means it doesn't increase, it doesn't decrease. It's all the same, right? So this one is saying 95% of the chance, if you test it like 100 times and 95% of the time, 95 times, you get somewhere in this range. And that somewhere in this range is actually containing the zero. That means it might be zero. So that's what this model is telling us. So therefore, it's, hey, let's not focus on that. Let's focus on something more significant. So that's the blue or red. So that information or that question that you can answer by using the information from this tab. And again, this is can be done only for the statistical model, not the machine learning model. Okay. Having said that, I'm going to create the machine learning model for this same data, for the same combination of variables. To do, instead of creating a scratch, I'm going to just copy this, selecting duplicate, and I'm going to name it random forest. Let's create the same, a similar model with different algorithm here. So I'm going to, once it's copied, I'm going to change to random forest. I'm going to keep the target variable, predictor variable in the same way, and then click on Run button. And then now here is a random forest model being created. But you notice though, as you notice, there is no coefficient here. So we have the prediction importance. So I can go to the importance and see, okay, what variables are important. And then I can go to prediction tab and how those variables are related to monthly income. But I can't answer, for example, hey, is this age, this seems like a flat, but is this significant or not? Attrition, this is significant or not? That types of things I can't answer. But machine learning doesn't care those types of questions. It's really about how accurate it can predict. What's the how to increase the prediction quality? That's really what machine learning is all about. The statistical learning model is, it cares about the prediction quality, but also cares about the relationship itself among the variables. So it's very like different strategy among two types of algorithms. So therefore, like we don't have the coefficient, but we have the similar information you can get. Okay. So, and then let's go back to logistic regression, linear regression. There's one last part of the analytics grammar of analytics, which is evaluation. Okay. So that is like you want to go to the summary. And then this is where you see, if you use this model to predict and what's the result would be. Then there are two types of data types we're talking about here. One is a numerical data type that we are using, in this case, the salary, right? So then you want to pay attention to these two. If you have to pick one, like I would recommend R squared. It depends what you want to do with it. But if you're using it in terms of like analyzing the data, not like a prediction itself, then R squared is more useful and especially more understandable. So R squared really is sort of like a measure of correlation per se. So the value ranges between 0 and 1, 1 being the most correlated or the highest sort of like related. But this one is really like how well this model is fitting the data. Or in this case, we are predicting the monthly income. And monthly income varies, right? Like from like maybe somebody is 5,000, somebody 20,000. There's a lot of different values. But if you use this model, how much of the variance of the income can be explained by this model? And when I say the model, meaning job level, working years, job role, and and all the valuable information. If we have this information, how much we can explain, that means how much, whatever the person, like it comes, and then this person's salary can be 15,000. We might not be able to predict it precisely, but if in all, let's say like 100 people, 1,000 people, in this case, 1,400 people, if we predict what's that sort of like a ratio of the variance that we can actually predict. So great, one is the best, the closer to the one, that means it's better. So let's take a look at this particular case. In this case, when I go to summary, the R square is 0.94. That means one is the best, right? One is the highest. So like 94%. 94% of monthly income can be explained by these variables. That means 6% we can't explain, and that might have something to do with random variance, or maybe some of the information like we haven't captured. Maybe how much time like an employee went out for like a bars and watch sports game with the boss, and that something like that. Who knows? But that type of information is not there. But at least given all this data, that we can actually explain how the monthly income changes. Okay. So another one is RMSE. This is like a root mean square error. Error is a difference. So when you predict, it's always there's some difference. The difference is you can go to digital tab, but there's a difference between actual values and predicted values. And what is the average, or what is the mean of that differences? When you predict with this model, that is 1,110. So if you use this model, and then there's a difference between the actual value. Let's go to the data tab. And then this person's, where is that? Here. First person is $5,993, but the predicted value is 5,966. So there's a difference between. And what is the average of the difference? That is not just one person, but all of them, right? And that is this particular value, RMSE, under the summary tab. Okay, so these are two things that you want to pay attention to, or you want to note. But if the target variable is logical, like converted or not, or quit or not, or something like that, then you want to see AUC. Okay, so the AUC this is a whole another topic. If I need to explain, I'm planning to actually do some seminar around AUC in the future. But today, let's understand this as basically this is similar to R square. It indicates how much correlated or how much associated between the target variable and a given predictor variable. Okay, so the range is not unlike RS square, ranges only from 0.5 to 1, but 1 is the strongest. 0.5 is like that weakest, almost like a no relationship. Okay, so it's really it shows how much that this model can separate the true data and false data by using all the predictor variables, or whatever the patterns that algorithm find in that data with these variables. Okay, so so that's really sort of like efficiency of separating the true and false. So that's AUC. So here this time, when you look at the oh sorry, this is the linear regression. So I have a screenshot that's here. When you see something like 0.85, that's pretty good, but not like 1. So it's not like 100% can predict, but at the same time, it's closer to like a kind of one side, not the 0.5. So it's pretty good by using these variables. Okay. So from here, the two things I like to cover is a correlation, causation, multivariate analysis. Is have you seen something like this before? So that's when you compare the shark attacks and the ice cream sold data on the time axis. So from May, June, July, both of them going up. And if you look at only these data, then you might think, oh, you know what? Like, so we want to increase us ice cream sales, so let's bring more sharks in the ocean and so on. And of course, nobody think that way because most of people think that, oh yeah, that's just random coincidence. And then right, so but when they're in this world, even with this data, when you see the correlation, we immediately think those are maybe like a causational relationship, not just correlation. Meaning, because increase of salary, increase of ice cream sales, like that's why like we get more people getting attacked by shark, or vice versa. But we have something called confounding element. So like it's actually temperature is the one who's causing increase of shark attack and increase of ice cream sales. The temperature increases and more people go into the ocean. Therefore, like we have a higher chance to encounter with the sharks, right? So so these are very important because when we look at the correlation, I don't think nobody, even the professor of teaching the causal relationship, causal inference in the statistics world, I often observe they keep making mistake on this correlation and causation. That means me too, like I always get confused as quick to jump to conclusion. But I don't think human beings are good at this thing. But anyway, but when you use the data, you can kind of organize if this relationship is a causational or correlation. It's not like 100% you can get the answer, but you can at least ask questions and answer by using statistical learning model. So in this case, let's say like we have working years and age, right, as a predictor variable. And we have built a model with a bunch of other variables as well, but like I'm very simplifying here. And then both of them looks like there's a correlation, meaning older you get higher income, and the longer years you work, and you get higher income. But of course, there is some correlation between these working years and age. By the way, in this data, these two are correlated, but it's not really the same because some people come join this company when their age is 40 years old or something like that. So the working years can be 5 years, but can be very high salary, right, compared to age. Okay, so anyway, but still, there's some relationship between working years and age. So in that case, if somebody said, oh, like higher working years, longer working years and higher income, and somebody always said, is that because just the age? Or it can be something else, like maybe the job role, like, or maybe something else in this data, right? So in that case, what's really happening is, in this picture, maybe the age is the one in this company like really have influence on the income. And so that means older people tend to have longer working years, right? And then therefore, and also like higher income. But if you're focusing on the result between the working years and income, like it looks like shark attack and ice cream. It's like both of them have some kind of relationship. Well, maybe though, not the age. Actually, working years is what it matters, not the age. Even like 45 years old, 20 years old, it doesn't matter. How many years you worked at this company matters, or that type of company. Then in that case, again, the longer working years tend to have older age. And then also in this company, we really care about the working years, so like income increases. So then we get kind of confused, like which one, working years is the one, age is the one, which one is, have an impact on the income increase or decrease. In that case, what we can do is we can keep one of the predictor variables constant. For example, let's say like age as a constant. Let's say like only 25 years old people or just 40 years old people. And then within that group, let's say like, there probably some difference in terms of the working years. let's say like working as 1 and 2 or 2 and 3 and so on. And if when that working as change in a group of 40 years old people, then there's a difference in the income or not, right? So then if there is, then obviously like working years have some impact. And of course, what about the other variables not in this picture? Yes, of course, you can keep asking those questions as well. But at least if we're talking about this very simplified, just working years, age, income, then you can kind of organize the relationship. Other things too, like what if what are the relationship between the age and income? Then like you can keep the working years constant, only the 10 years of working years group, and then there probably like the age difference in that group. And when the age changes, does income change as well or not, right? So then we can answer these type of questions. Okay. So in order to do this, this one is, again, a very simplified, but usually like what you want to keep constant is not just one variable. You want to make it 20 variable constant and only age moves, and then like you want to see how the income changes. And for that, something like that, like multivariate analysis can help you answer these questions. But this one requires a statistical learning, not the machine learning models. There's some like papers and kind of trying to do the similar thing with machine learning, but so far it's not yet becoming more reliable or real world example. Anyway, so you can use the multivariate analysis. So that's what we actually have been doing here. So when let's go back to this linear regression, and then see this like predictor variable. I'm gonna actually do what is not multivariate, right? So like I'm gonna just duplicate and then create another one, and then still a linear regression, target variable the monthly income. But here instead, I'm gonna clear all the variables out. Okay, and then if I select only the working years, I think that here, total working years, and I click OK. And then like, if I run it, so this is something called simple regression or univariate analysis, because there's only one predictor variable. And if I go to the prediction tab, this is a prediction by variable. You see this one, like working years, gray is the actual values, and blue is almost like going through the middle of the actual values, right? It's really nicely fit line with the actual values. Okay, and then like when I move the mouse here, and it shows the coefficient, which says 467. That's a second from the top in the blue box. Okay, so that means the 1 year increase in the working years, then you can expect $467 increase in the salary or the income, right? But then somebody asked, like, hey, maybe that might have something to the job role, that might have something, like a job level and so on. So that's what we have done. This one, going back to the analysis with a multiple, like a bunch of predictor variables. This case, okay, this one is like we have the bunch of variables selected, predictor variables selected. That means if I go to the prediction tab, and then where's the total working years here? Let's take a look at this second from the top. It says coefficient 45. You remember previously, like when we had only working years as a predictor variable, we had like $460 something there. But now it's only $45. That means if you have 1 year increase in working years, you can expect only $45 increase. And what's going on? Well, that's because job level, job role, performance rating, and all the other variables, if those are the same, only the working years is the different, then you can expect that much. So that means when we saw here, this one, we had only total working years is the predictor variables. This total working years carry on other information like job role, job levels, and so on. Let's say, for example, maybe total working years is like 30 years and 35 people. These people tend to be job level is 4 or 5. Or maybe the job role is manager or research director or something. That's why that means this line is not really reflecting just the total working years, it's carrying on other information. But when we did the multivariate analysis, that means we actually make other variable constant. And then what happens if only the total working years change? So it's not like fitting the actual values, but it's more kind of getting close, right? So now at this point you wonder, okay, so this is kind of getting flat. So that means like it doesn't matter, maybe like just $45, who cares? It's like just a small amount. And then if you want to answer that type of question, again, go back to the coefficient. And then take a look at total working years. Oh, okay, this is still blue color. So that means it's not like nothing or a marginal thing. There's something there, but it's very small. And this is the reason this blue line and the gray color is kind of diverge as the job level increase here, or for example, certain job roles. That's because job level 4 or 5, probably these type of people tend to be manager, and maybe working years is longer. And maybe that's why it's not like just a job level that can explain why job level 4 and 5 people are like a high, this much of the high income. Okay, so again, the statistical model, this case a linear regression, but even like a logistic regression for survival analysis, the Cox regression, it's always the same. When the other variable is the same, and if only in this case job level 1 increase, then how much you can expect in the increase in this case monthly income, an increase in the probability of other odds ratio in logistic regression case and other algorithm type. Okay. So, and the other thing is here, the importance is going back to which variables are more important. In this case, we saw like job level and job role, those two significantly important variables. When we go to the random forest here, and then when I go to the importance, and here is like a job level is the same, both of them, linear regression, random forest, either way, job level is very important, right? It's almost like a nicely correlated to monthly income. But when you look at here, age is the fourth important. And somehow it's it's not like almost nothing like attrition, but it's actually there's some degree of importance. By the way, I forgot to mention what's this y-axis value means. I get this question a lot. So this is a relative value. So it doesn't really mean anything of this particular value. It's just a relatively compared to job level and the other variable, how much more important. So that's what that y-axis is. But anyway, so here's the age. And then when I go back to the linear regression, and look at the age here, there's no even box here. Like if I scroll really, really small, then there's a little bit of bar, but it says gray, not even significant. But the random forest somehow is showing the blue bar. And again, machine learning doesn't do those significant tests. So there's no way to make it blue or gray, that kind of stuff. But not only that, machine learning, what that machine learning model doesn't do is to keep other variable value constant thing. Okay, so machine learning loves correlation. Any correlation, even the fake correlation, whatever that is, it will use it as long as it helps to predict the value that is closer to the actual value. That's what the important thing for the machine learning model. Statistical learning, it's not just about the prediction. It's about, hey, is this relationship significant? Is this relationship really something when the other without by excluding any influence of the other variable? So it's statistical stuff is more I don't know what that word can be, more like robust, maybe you can say, more reliable in terms of data, analyzing the data. So that's really the difference. Then when you see like important stuff, yes, machine learning, statistical learning model, you see these important steps in either way, but the information is something different. And maybe the ranking is also different. And then that difference comes from that fact that statistical learning model is the only one keep other variables constant. Okay. So having said that, other thing, it's just a difference. I was talking about the statistical learning and machine learning models different. So statistical learning, those are kind of linear regression, logistic Cox regression stuff, and machine learning, decision tree, random forest, XGBoost, and others. Behind the scene, the model of the statistical learning model often is a formula. Y equals something X plus something Y, something X2, and so on. Machine learning is more like you just imagine like a bunch of if-else statement in a programming code or something. So that's in a very nutshell, but the difference. And then here's a difference table. So, but statistical learning is not good at finding a relationship in a non-linear relationship. So that means, for example, in this case, like pretty simple data, like job level goes up and then income goes up kind of stuff. But what if like job level goes up and then income increase, but then after a certain point, income stays or income actually deteriorate or something. In that case, the statistical learning model is not really good at those non-linear type of relationship, but machine learning is pretty good at it. It can capture that type of patterns. And then the second point is that, like I have said, it's like an ice cream and a shark attack example. So correlation and causation different. And machine learning cares only about the correlation. They use any correlated information to build a model. But statistical learning is not really about the correlation. It's about, it's not necessarily that you can find a causation answer, but also it's very useful when you want to organize a relationship to answer causal questions. And then the significance check, the statistical learning, yes, it does, but machine learning, it doesn't. Okay. So non-linear relationship is something like this. Like x-axis is working years. So as if it's you use a random forest, it really changing the slope of the blue line. So there's no such thing as slope in a random forest world. So it tried to mimic the actual data. So it can capture the non-linear relationship, but the problem is you never know if that's a fake correlation or not. Okay. So that's that. That's pretty much it for today. So let me summarize today's what we have done. So grammar analytics is basically these 4 steps: so variable importance, prediction by variable, coefficient only for the statistical models, and then evaluation. As long as you know this, and then you can actually master using all the prediction models in Exploratory. And then all the prediction models, again, it really depends on what the data type you're interested in. So like you're interested in numerical target variables or logical time. And then you decide which algorithm to use, either statistical, machine learning. And then, but again, you have the grammar of the analytics. The information you should look at is always the same. Okay. So you can build a prediction model by having an algorithm define the formula or a set of rules based on the pattern it identifies in data. In most cases, rather than using such models to predict the future, it's more useful to gain insights from the models in order to make better decisions. Okay. How the prediction models are made, the inner working of the prediction models are different depending on what algorithm you use. But it's all the same in terms of like algorithm trying to find the patterns in the data and then define the model based on the pattern it finds, right? So that means what we as a user of a prediction model is that what we want to do is we want to understand the patterns in the data. So that can be extracted, the insights about the patterns can be extracted from the models in a consistent way if you use the grammar analytics. And the Exploratory, you have that. So it's always you see the same set of tabs. Okay. And then there is one big difference between statistical learning model and a machine learning model in terms of interpretability. Statistical learning model can help you evaluate the significance of the relationship between the given two variables, between a target variable and the given predictor variable. And also you can go beyond just the correlation. You can start drawing a picture of, hey, wait a second, is this like a really increase of ice cream, like a really cause a shark attack or no? If you happen to have the temperature data, you can bring in and then you can differentiate that, clean up the relationship to build the better hypothesis about the data. Okay, that's it for today. So one sort of like not, I wanted to have some announcement. So we have released the Exploratory 6.11 recently, but also last week we released the patch version like 6.11.2. So with this, especially something like a case conditional calculation dialog can be much easier to use, and the product itself is more stable. So I would recommend you guys haven't done so, like go to the download page, our website, and then you see the download menu. Under that, you can select Exploratory Desktop, and then the latest version is 6.11.2. If you want to see more details and what are the changes, then you can go to release note to check the details as well. Other than that, I'm going to create a recording of this seminar, but not just this one. All the past seminars recording are available. And also you can check like what's coming in the future from the online seminar page. And also, if you want to know like how to use Exploratory, we publish a bunch of how-to tutorials and also video as well. Okay. Otherwise, if you have any questions, please send me my email, or we have the Twitter. We make announcements about Exploratory pretty often at Exploratory Data. So please follow as well. Okay. That's it for today, and we have already passed the time because of like I was not sharing at the beginning. So apologize for your time, wasting your time. But again, thank you for joining today's seminar. I hope you enjoy, and I hope you're gonna have a great rest of the week. Okay.